This lecture is about filtering. This figure shows the heat consumption in a major city, and you can see that there is a clear trend to it growing, and there's some kind of cycling going up and down. That would be the weekly cycle of the heat consumption in that city. People go to work, and then there's weekends, people use less heat for the industries, and so forth. This figure here shows the temperature outside, and as you can imagine, there will be a strong correlation between the two. In fact, if I were to plot the air temperature and the heat consumption versus each other, you can see that there's almost a linear trend between the two. So that means that I would be able to seemingly predict the heat consumption by just taking the air temperature and multiplying it by some scalar, and that way I would get the heat consumption. It seems reasonable enough, although of course there is a bit of a spread, so that there's a little more to it than that. If I use the air temperature and compute the appropriate scaling and use that to predict the heat consumption, this is the difference. This is the error between the actual measurements and the model that I used to estimate it. And as you can see, the error contains some structure. There's still some periodicities and trends in it, and I'm not really capturing all the details. If my model would be perfect, this is what it should be looking like. Then my model error should be white. There is no further structure in the residual. There's no further structure in the model error that I would be able to exploit to make a better model. If I look at the first case here, you can see that there's clearly the weekly cycle still in there. So I should be able to improve my model by adding some kind of structure that captures that. Whereas down here, there is nothing. There's just noise, meaning that there's no information that I can use in this data that could allow me to improve my model. This is what we strive for. We want our model to be such that the modeling error is a white noise. In order for this to happen, we have to extend our model so that it is more than just a scaling. And the way we'll do that is that we'll treat it as a linear filter, meaning that we will take the input signal here, in this case the temperature, run it through a linear filter, and out we get the heat consumption, that is the output. So now what I'm interested in is to find the representation here, the filter H, that is such that I can take the air temperature and create a model of the heat consumption, capturing all of this energy. But to be able to do that, I need to know what happens when I take a stochastic process and filter it through a linear, stable, causal, and time invariant filter, which is what we are restricting our attention to. And of course, then we will start by saying, what does it mean for a filter to be linear? Well, it means that if I take the input, scale it, and add another input and scale it, I will get just scaled versions of the output of the two. Similarly, if it's time invariant, that means that if I delay my input a little bit, and then the only thing that will happen is that I will delay my output similarly. That the filter is stable means only that it doesn't explode in your face. So if I put a limited input in, I will get a limited output. There's not going to be an exponential increase in my output in some sense. Causal only means that there is nothing going to happen before there is an actual input. So the filter will not start to generate material outputs before there is something actually input into the filter. In the case of a discrete time filter, we can write the output as a discrete convolution of the input and the linear filter like this, or alternative, just rewriting it so that the delay sits on the x input instead. That means that the mean, and that means that I'll take the expectation of full thing, I can move the expectation in, will be the mean of the input times the gain of the filter. H0 here is the Fourier transform of the filter evaluated at frequency 0. That's the gain of the filter. That's the amplification of the filter in itself. An important factor to note is that if the input is a White-Sand stationary process, so is the output. And if the input is a Gaussian process, so is the output. Looking at the autocovariance function, you can see that this will be turning into a double convolution. Recall that the power spectral density is the Fourier transform of the autocovariance function. So that means that I will get the power spectral density of the output by taking the power spectral density of the input and multiplying it by the magnitude square of the filter response in the frequency domain. I can similarly define the cross spectral density by just taking the Fourier transform of the cross covariance between the input and the output. And this will give me in frequency domain the so-called Wiener-Hopf equations, which, if you look at it, that seems to suggest that I should be able to get an estimate of the transfer function by estimating the cross spectral densities and then dividing by the auto spectral density of the input. That means basically that I would be able to estimate the spectrum of the input. That is, I'll take the Fourier transform parallelogram of the time sequence, and then I'll compute the cross covariance between the input and the output. That is the temperature and heat consumption. Take the Fourier transform of that, and that I will just get the quote of that, and I will get an estimate of the transfer function. In theory, this would work perfectly well. Reality, regrettably, this doesn't work at all. And the reason for that is because of the high variability in the parallelogram estimate. You can basically not estimate the cross-spectral densities and the auto-spectral densities of the input and the outputs and the cross between them accurately enough for this to be a reliable estimate in practice. So we will need to have better methods than this.